Me now?
Yeah, perfectly fine. It just happens in between.
Mm-hmm. I'm sorry, I guess there's no way I can improve that. Sometimes it's just because of the internet. If that gets serious and you missed some part, please ask me. I will repeat it. Okay?
Okay, thank you, Professor.
Thank you. Yeah, so we said that this in here scripting languages, which these days people are more interested in, like Python. You can do Python coding here. Every single line of code you write here will get executed, and the we said that the interpreter is doing that. So every single line of code gets executed, and you will see the result. Basically, your code is limited to each line of code that you're writing. But it's not like that in compiled languages where you have to write the whole program and it has to run from there. Okay, are we good? If you have any questions so far, please just unmute yourself and ask. Very good. Question number 5. Which one of the following programming languages is an example of a low-level programming language? So the same thing. Which one of these basically can run on without the need for an operating system? And Hushi will answer that. I think you're back, right? Hushi's offline. All right. Let me pick another person. Simrat. Simrat will answer this question, please. Any thoughts? Simrat's not there. Uh, okay, not more than two people. This is Objective C. All other programming languages require operating system except for Objective C, which is kind of C. Question 6. What was the first killer app? This I'm gonna answer myself. A killer app was the basically the uh, Excel, the very primitive Excel that Apple wrote, and that became the first time that in offices, just because of this app, people realized that having a computer is a must to have. And that was one of the very successful apps at that moment. It just basically what it did, we had in our slides, what it did was it just it just created forms. You could put things, items in the forms, some numerical data like price and stuff like that, and it could do the calculation for you. And question number 7 is just a match, so this I'm gonna do myself. Python, we said that is very rich when it comes to Bijoy. Yeah, see, Python, it comes the power of Python is basically it's very close to reading and writing English sentences and reading English. So the power of it is its readability, basically. uh, um, and it has a lot of libraries that almost does everything for you. So Python is created for code readability. A would be a correct answer for that, I guess. Java and JavaScript. We said that Java and JavaScript are not the same programming languages. JavaScript and Java, we explained the differences, so I'm not going to repeat those differences. We had in our slides, and so Java and JavaScript are not the same. C would be the correct answer for that. And platform is important to understand what we mean by term platform. Platform is not just the hardware. It's a mixture of your hardware and operating system. That's the platform you have. This will become important in our today's lecture. Uh, so platform is OS and hardware together. Go-to was outlawed. So we said that when in 1970s, by when C emerged, structured languaging became popular, and that was when people said, okay, like whenever we are using this go-to, uh, after like after 200 lines of code, everything becomes a mess. So they they said that it's forbidden. So nobody should use go-to anymore these days. So that was outlawed by structured programming and compiled languages. Uh, we said that we have compiled languages and interpreted languages. Compiled languages like C, you need to write the whole code and then the compiler compiles that to machine code and gives you an object file or an executable file so that you can run your program. They are fast because the whole thing, like the compiler, has a bird view of your program because it has everything it needs. It has the totality of the program, and that's why it is fast. Things are much more structured, uh, but they are less flexible than other programming languages. For instance, in Python, you can declare a variable, and then uh, without knowing even or knowingly, you can change. For instance, there is a variable that's an integer. Then you can knowingly or unknowingly can put a float in that. Like, it's fine. But you cannot do that in C. You cannot do that in C++. You'll receive a compiler error. You cannot even change the type of a variable that you have defined. If you define integer a, line 5, in line 5622, you cannot say float a. A has been declared there. Obviously, if it is in the scope and all things that you know about the scope, if they are in the same scope, you cannot even change the type. So they are less flexible than interpreted languages. And question 8, uh, which of the following programming languages was not developed in the 1950s? A pure history question, which is C. So C developed in 1970s, and C is the answer. Okay, very good. Are we good so far? Are we good so far? Meanwhile, we have a message. Okay, it's not from class. Victor, you said no. Do you have any question?
Yeah, on question number 5, the low-level programming language,
Uh-huh.
is it? Can you just elaborate a little bit?
Yeah, low level languages are an other word for that is embedded languages. They do not require operating system. You can use them purely on hardware. So if you become a system programmer or firmware programmer, they call it. This is the title for that in industry. You will develop firmwares. What are these firmwares? These firmwares are piece of code that are written to directly interact with the hardware. Uh, example for that are hardware drivers when you are adding a new hardware. So when you're adding a new piece of hardware, uh, there is a firmware that is low level language, and that firmware directly communicates with the piece of hardware that you've added recently. uh, we have C, for instance, we have Objective C, uh, and even C plus. No, just basically C can be used for that. They are capable of communicating directly with the hardware. So we call those low-level programs. Like Python cannot do that. You can't even use Python if you don't have an operating system, a running machine with an operator. But you can write a C program code and load it to a, for instance, Bluetooth module, and it can directly communicate with that module. These are more difficult to develop. Why? Because you have to have the knowledge of hardware and how to write the code for that hardware. But when we are doing, that's why higher level programs emerged, like C++, Java, Python, and all those high level programming languages, because it was difficult. For instance, if you want to if you want to allocate a memory, if you want to do some memory stuff, if you're doing C and low level C directly on hardware, you have to go check the data sheet of your hardware to see the exact load address in hexadecimal, in numbers, for the piece of for the piece of memory that you want to store your program, or you want to read some variable, or just load something and do some arithmetic. But it's not like that in other high level programming languages. Still, C is also can be done in high level, can be considered a high level language, because you are writing C code on Visual Studio, and Windows takes care of other things. But that can also C is basically at low level. It was basically developed as a low level programming language, and it wasn't until the development of operating systems that this also became a programming language that you could run on Windows, or like other operating systems. So yeah, basically those programming languages that can directly communicate with hardware are considered low-level programming languages. Yeah, going back to the memory thing, if you want to do something with a variable, when it's in C or C++, that's running on an operating system, you don't even need to worry about the address that it's being saved or read. Like pointers, for instance. If you look at pointers, pointers are exactly inherited from those old days that C was used directly on a piece of hardware. So that address pointer is an address of a variable, not the variable itself. And that pointer we have in hardware. In hardware, registers can keep the address of a piece of hardware that your data is stored in there. And still we have pointers. They come in handy. They are very useful. But when you are using pointers these days, you write your code in Visual Studio. You don't care what exact address is being allocated to that pointer. You just know that it's a pointer pointing to variable A. But in reality, it wasn't like that. So that pointer's exact address used to matter, and still matters if you are programming for hardware, uh, if you don't have an operating system and you're just directly dealing with hardware. I hope I answered your question. Was that good?
Yeah, that's good. That's good. Thank you, sir.
Great. Thank you. Let me see. Okay, so I think we spend a good amount of time on reviewing these stuff. If you have any questions, please just go ahead and ask. Let me just publish this poll. Okay. How about no? Is it too soon for a break? Let's just start a poll. Uh, is it a good time for a 5-minute break or not? Please answer. I see a lot of no's. Oh, yes, people are coming. 5 to 4. So how about those people who don't have any idea? Let's continue. All right, let's continue, and I will give you a break after a couple of slides. Let's continue. Okay, very good. Let me pull up my slides. And if you want to leave, yeah, I want to leave. And here are our slides. Okay. Let me also make sure I have paint.
Professor,
Yeah.
Professor, I just need to know we have to do like 10 out of 11, right? Activities. Actually, I missed one.
Yeah, you have to actually do 9 out of 11. So you can you can even miss one more. But don't miss it, obviously. Just to know that, yeah, 9 out of 11 will be enough. Okay, one more time, slides. Okay, so as I said, today we're gonna see some very interesting things that probably you haven't seen before. They are interesting because they are kind of showing the limitations of C programming or any other programming languages, mainly in C, we will discuss, uh, because of data types and the way data is really stored in memory. So we will see binary decisions. We will see. We will discuss what binary is and what is the opposite of binary. Why do computers need binary? Why do we care? Why do we care? That's the main question. So that will take us to some piece of codes. I will show you. We will go through the codes together and see what happens. Um, and how can we use and why do we have to know this and how it comes handy when we are writing programs, bugless programs or debugging programs. And then we will take a look at hexadecimal representation of numbers, because hexadecimal numbers are things that you these days, the where do you use these hexadecimal numbers is usually color, giving color style to in web design. That will be a direct example, but hexadecimal is a very commonly used number system for showing so many things, especially in low-level languages. So we will see some examples of hexadecimal uh, in creating different colors. today you will need a calculator, and it's good to use your machine's calculator. I will tell you why. Well, let me tell you why. If you just pull up your calculator, uh, if your machine is Windows, I guess many people's machine is Windows. Am I recording this? Sorry, let me make sure I'm recording this. Let's close this. Am I recording? Yes, I am. Very good. And good. When you pull up your Windows calculator, you can define different configurations. It can be a standard calculator. It can be a scientific calculator. Now you see you have different capabilities to calculate many mathematical stuff. It can be graphing. You can plot graphs, do lots of good things there, or it can be the programmer configuration. So in the programmer configuration, uh, you see the keyboard, and the default is on decimal numbering, decimal numbering format. But you can change that to octal, to binary, and to hex. And you realize that uh, based on what numbering system I choose, some of these keyboard keys are getting are becoming inactive. Uh, there is a very good justification for that. Uh, so from in decimal, we don't have A, B, C, D, E, F. But when I choose hex, they also become active. It means um, base hex base of hex is 16. So any number below 16 can be used for representing a hexadecimal, sorry, not hexadecimal, a hex number. And they are 1 to 9, we know, but but to avoid showing 10 with two decimal digits, they say after 9 you can use A, B, C, D. So this is 10, 11, 12, 13, 14, and 15, because we need from 1 to 15 to represent hex numbers. Don't worry if you have no idea what I'm talking about. Don't worry, you will see this in 5 minutes. If in binary, to represent any number in binary, you need anything. Binary's base is 2, right? So hex base for hex is 16. Base for decimal is 10. Base for octal is 8, and base for binary is 2. So when the base for binary is 2, you need any number less than 2 to be able to represent a number, and they are zeros and ones. And that is why we are interested in binary. So please go ahead and pull up calculator on your machines, and select programmer so that we see this part. We're gonna be doing some calculations, some stuff, some concepts I will explain on this calculator. Okay? Are we good with this? If you have any questions, please just let me know. Okay. Coming back to to our slides. So you will need a calculator today. We will work on integer sizes, different type of integers, signed, unsigned, character, stuff like that. Character is an integer? I think it is. I'll show you. Identify and solve integer overflow bug. What is overflow? I don't know. I will explain in 10 minutes. Right now, I have no idea what an overflow is. Work with colors. So this is the easiest part. This is the fun part. At the end, we've put it there to have fun a little bit at the end. Okay, humans understand something that is very different. That's the opposite of binary in data science, in whatever science. Binary is basically, if you want to give an example of analog and binary, analog is anything uh, real, is anything you see in real world. You count from 1 to 10. You see light, not just it is in different intensities. During the day, different levels of light intensity you see. It's not like either light is maximum, so we have sunlight, or it is during the day it's sunlight, or there's no light. It's not like that. It's not just zeros and ones. We have a spectrum for anything in real life. We have a spectrum for speed. We have a spectrum. It's not like your car car is either stopped, or it's going in like 100 kilometers per second speed. It's not like that. So in real life, time is not binary. These are, they call these things analog. So analog stuff have a spectrum of quantities. But in contrast, binary can only be 0 and 1. And that is what our computers, what our hardware, what our computers can understand and work based upon. They cannot understand analog things. Computers can understand binary, can understand what's called digital. Why? I will show you why right now. But so in contrast to binary that computers understand, which is either something, that something in computer world is a bit. That bit can be a bit in a CPU's register, or can be a bit in computer's memory, uh, or can be a bit on your external device, or can be a bit in a piece of hardware, uh, in the hardware of your mouse. Anything in computer has bits, and those bits can be either 0 or 1, black or white. There is no gray in between. There is no color in between. Nothing. Just zeros and ones. So this creates some complications. It makes it a little bit complex to understand. That's why when I showed you 2 weeks ago, when I showed you a machine code that the compiler generated and a C code, you had no idea how that nice readable analog, maybe I can call it analog, piece of code converted to that binary zeros and ones, which nobody could understand except for your computer. So this makes a big difference, and to some extent, not everything, about binary, but to some extent we need to know as programmers to avoid some kind of issues that might happen. Uh, Numbering system, that's why is important. Numbering system is shifting from the analog good old real world. We can count uh, in decimal 1 2 3 4 5 6 uh, to the binary world and its variations, which are octal and hex, which I will explain why. So uh, now we are in year 2022. How many different ways we can use to represent this 2022? Obviously, we can have any base. We can have base 521. We can have base whatever you like. But the most important base that we represent our numbers with is 10. What do we mean by base? Can somebody tell me what we mean by base when we say like this is base 10? We want to show this number in base 10. What does that mean?
By 10.
It Mudit, could you repeat your answer, please?
Sir, base 10 means like the digit with which we have to multiply with.
Yeah, it means if you imagine we have, yeah, that's right. Um, to give you a more tangible explanation so you can understand is imagine you have 2022 uh, chopsticks, okay, and to you've seen in movies people in prison, they when they want to count, they just they just make scratches on the wall for every single day, and then they when they reach to 10 of those they scratch another one, making that a group of 10. So people have done this. So if you're making, to be able to count a number, if you're making groups of 10 things, that is base 10. It can be groups of 10. If your number is larger, it can be groups of 100 things, 10 to the power of 2. It can be even if your number goes larger, it can be you can have groups of 1,000 things, uh, and so on and so forth. So when we are doing this grouping based on groups of 10 things, that becomes base 10 representation of a number. And that's what we know. As human beings, we know base 10 intuitively. Now, let's see what will be the representation of same 2022 in base 16. In base 16, so you might think that, okay, now I have to make groups of 16 things. And if my number is larger, I should make groups of 16 to the power of 2 things, or 256 things. Here it was 1,000 things, 100 things, 10 things, or nothing. 10 to the power of 0 is just 1. Same here. 6, but here the grouping is different. So 16 things, 16 to the power of 2, 16 to the power of 3. So when we are showing, so it means 2000, here it means 2022 things. If I had 2022 chopsticks, if I had, I would have 2 packs of 1,000 chopsticks, no pack of 100 chopsticks, 2 packs of 10 chopsticks, and 2 chopsticks. Here, same thing, same number, 2022. You have 7 packs of 2000. You have seven packs, each having 256 chopsticks. You have, remember, A, B, C, D, E. E is 14. 14 packs of 16 chopsticks and 6 chopsticks. That's how we understand this. And if we continue this same with, if we want to have base 8, and finally if we want to show in binary. So in binary we have packs of base 2. It means pack of 2, pack of 4, pack of 8, pack of 16, pack of 32, and so on and so forth. Why is it even important? Because computers understand this form of representation. Again, why? Because, let me show this. Because current computers hardware is dictating that. If we were talking about quantum computing, what I'm saying would be nonsense, because there we don't have only zeros and one. We have millions of states, and that's the power of quantum computing. But now that we are restricted to these computers, to this kind of hardware, that's the hardware that is dictating that. Why? Because my hardware, my bit, can only accept 2 states. It's a switch. It's a two-way switch. Every bit is a two-way switch. If you connect that to 1, and at the same time only one of them can be connected, you cannot have both 0 and 1. So if this switch is connected, your bit is showing 1. If the other bit is connected, your bit shows 0. So now I can distinguish between 0 and 1. There is no 2, 3, 4, 5, 6. And this is a big limitation that limits every single calculation and representation to base 2 or binary. Is that clear? Is what we said so far clear? Sorry, I was supposed to get a... Is what I said so far clear? So if you say no, if you don't answer, that means you have to ask a question. That is why we need to know something, not everything, about this binary representation. And for binary, we need to know how we convert to binary using our calculator here. So in our calculator, you can see the binary representation of your decimal numbers. If you put to decimal, I want to know the binary equivalent of, and basically all those equivalences of 87 in decimal. If I put 87 in decimal, that will equal to 0101, 0111 in binary, 127 in octal, and 57 in decimal. This is how we convert this. If you want to do the conversion from binary to decimal, you set it to binary, and you put your number here. What's that? Like, I want to know what 101010 represent. It represents 42 in decimal 5-2 in octal, and 2a in hex. So we use our, you have to do divisions and multiplications to 2's powers, but that's once, now that you have this tool, I don't want to bother to say like do this to do that. Don't want to bother. Just use your calculation. Are we good with this? I want to know the decimal equivalent for a binary number. I just put my binary number here. So this binary number is equal to 95. And if I want to convert from decimal to binary or any other base, I just put my number there. So 9658 is equal to this guy in binary. Published poll. 9 out of 17. Those people who are not here will miss some of the interesting parts that are just coming. Okay, any questions? So now that we have these numbers and computers can understand numbers only, how about text? How about letters? We are a significant portion of what we do is with letters and numbers. So ASCII code was an effort to be able to enter letters and text to computers, introduce these to computers by assigning numbers to each one of these characters. So for instance, we have some special characters. Some of them, you know, for instance, this is delete, this is space, and other characters, ampersand, asterisk, mm, other characters that you're familiar with, and numbers, not numbers, like character 0, 1, 2, they also have their own code. So this part is the decimal representation of ASCII code for that letter. What does it mean? It means when you are defining a byte and putting V in that byte is 8 bits. When you are putting V in that byte, what gets really stored in there is 118. And if you want to know how it gets stored in there, you have to look at its binary representation, which is, so V gets stored as 118 decimal. 118 decimal is 011101110. This is what really gets stored in your byte. So in your byte, the LSB, this is LSB, least significant bit, this is MSB. So MSB is 0, then after that comes 11101110. So these bits are connected to zeros and ones in this pattern. And this is what is stored in your computer. But when you do an output, you see V, you see whatever, a character, one of these letters, a character. Does this make sense? Have you started thinking about this so far? How does it feel? Does this make sense to you? I want to know how many people say yes. And please just unmute yourself and ask question if you want, because I'm just gonna show you a piece of code on Visual Studio right now, C code, and that requires you to understand this first. 8 people said yes. Dishdeep is not here. Gormahak is not here. Parvinder Jeet is not here. Paul is not here. Abdullah is not here. Abdullah Muhammad is not here. Dishdeep, you're here, but I think you didn't answer. That's why I thought you're not here. Okay, good. Very good. So this takes us to our next slide. So now look at U. This slide is about character U, uppercase U, and uppercase U, if you track in this table, is represented by 85, decimal 85. Let's see what that decimal 85 is. That decimal 85, if I put it in my calculator, 85 is this. So let's see. Now we're basically asking you, or asking ourselves, if what you see, in a piece of memory like this is, imagine this is a piece of memory that is keeping 0 1 0 1 0 1 0 1 0 1 0 1 0 1, which is 85, decimal 85. So how could a computer know if you are looking at an ASCII code, a representation of a character, or the number itself, which is 85? That is when type definition comes in our program. So the answer for this, that it is both. And how should we distinguish between these two? That is to us as programmers. Now take a look at this. Take a look at this code. I have a piece of code here that I want to share with you. We will see some interesting things here. I have commented out. I have to comment out the parts that we want to see the results. So this is comment. This is comment. This is comment. Here I have defined an integer named this to be 85 decimal. If you don't write anything, if you just put your number there, compiler assumes that this is decimal. Now, if I want to represent this, how can I distinguish between a character and an integer or a decimal number? So, for instance, in printf function, that's why we have different placeholders, because we literally don't have character, people. What we have is just these integer numbers, and we have to make everything else, even float, even text, even character, even whatever you think, out of these zeros and ones stored in a piece of memory. So what we have is basically everything we have is integer, but the way we interpret them, the compiler interpret them based on our code, makes a big difference. Now, if I run this code here, the placeholder is C, so it is telling the compiler to read this 0101010101 piece of memory as a character. Now, compiler goes and looks for the table and finds what letter this represents. But here in the second one, it just interprets that as an integer. And if I run this, the output of my program is here. Let me bring it in here. You see, this is the output of this line. This is U. This is capital letter U. And this is 85. Why? Because I gave different meanings to these things. But for my computer, if you just go inside your memory and look at this, you will not see any difference there. You will just see 01010101. That's what you will see. But how we interpret these with code is different. Same thing. Now let me close this. And now I'm defining, I have to comment these out. I am instead of a character, now I am instead of an integer, I am defining a character. Character that is capital letter U. And I have the same printf with same placeholders over there. What do you think will happen? Please answer. Gia, please answer. Give us your thoughts. Do you think there is any difference between this piece of code, as we have defined integer here 85, and this piece of code? What kind of differences we should see when I run this in the output? Okay, that is totally fine. That is totally fine. Any other person? Has anybody here has any thoughts about the differences or similarities, or basically the output that we will see if I run the code now? All right. If nobody knows, let's run and see. They're literally the same. So the output will literally be the same. If I put it here, yeah, the outputs are literally the same. See, I have defined integer 85, and I have showed it with character placeholder and decimal placeholder, and then I have defined character that capital U, and I have shown that with in printf with C placeholder, character placeholder, and decimal placeholder, and literally they are the same. Why are they the same? Because your computer doesn't understand what really gets. Mudit, you want to say something?
No, I'm sorry.
No, it's okay. It's okay. Actually, you make me happy every time you unmute yourself. You make me more than happy. I like we have discussions, because no matter if I do this or this in real life, in computer, inside the computer, what is getting saved into that piece of memory is 01010101, which in binary is a representation of 82. That can either be an ASCII code for you or can be number 85. That's why I don't see any difference between this piece of code and that piece of code. Does this make sense? Um, let's do a polling. Um, publish this poll. Um, is it weird? Does this make sense? Or I didn't understand. Guys, I want to know your answer, please.
Logic behind this, maybe I'm not correct. Is this right? Like, if we write even the integer or the character, but the ASCII code is same for the integer and character.
That's exactly correct. Because uh, because the ASCII code for this capital letter U or the binary code for 85 are the same thing, 010101, and that's what in reality gets stored in your computer. That means they are in its root, in its bit representation. These two are the same thing, but in this one, by printf character placeholder, you interpret that 01010101 as a letter, but in this one, you interpret that as a number. That's why you see different output when you are interpreting that same piece of code 01010101 as character. You see U. When you interpret it an integer, you see 85. That's exactly why this happens. Are we good now?
Yes.
Okay, wonderful. Bear with me. We will see more nonsense today. And this all exists in C programming, C++ programming, and any programming language. Just bear with me. If you don't know these things, you will be more shocked today. So what if I want to, okay, I guess with the poll, we're good. Publish poll. I didn't understand. Who said I didn't? I think it was muted. Okay, so we explained that. Now, I'm gonna uncomment even more stuff here. I'm going to uncomment some, comment this part, and I don't want this part. Now I want to comment it out. And now the same thing, guys, I can have integer hex, named hex. It's just a name. And now this 0x shows the hex representation of this. Now look at this. If in my calculator I look at hex for that 85, it is 85 was decimal. I can put 55, 55 in this format by adding 0x, which tells the compiler my number is a hexadecimal number. This again, the same thing. Again, this binary will be written to my memory, to my piece of memory. And when I run this, so now the answer probably to this question, what I'm expecting to see, is the exact same thing, because this this results in writing 010101 to memory. Same here, same here. So what if I run printf again as character and decimal? I will see the same thing. No matter how initially I wrote basically, or I defined my numbers. It was either, so now look at this, U85, U85, and again here, U85. Exact same thing. But this one is now, this is integer, input is decimal, this is character, input is the ASCII code of that character, this is integer, the input is represented in the form of hexadecimal. Now look at this. Now I want to comment this out. This one. Now, again, integer, another integer named binary, and this 0b, 0b shows that now I'm storing in binary. I'm talking in binary. And this is how you do this binary. And if I run this, I will see the same thing. Let's run it. The exact same thing. U85, 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 U85. So it doesn't matter. What matters to computers is what has been saved in binary and the way you interpret that binary. This is important for computers. And now, because look at this dat. Wasn't that a character? So how come I can do plus plus to a character? Does it even mean plus plus means add 1 to my number, right? When I say int x is 1, x plus plus, it means add 1 to the value of my x. It was 1, now it will become 2. But because there is no difference in characters and numbers, you can even do plus plus to characters. That was a character, and if you look at the if you in alphabet, what comes after U? V, right? Capital V. So by doing this plus plus, the ASCII code of this gets plus plus, and what I see is U. If you look at this, come on, every time it's running it here. If you look at this, now after U, this is the result of this guy. V. Now, the ASCII code got incremented by 1, and when and no matter what type you have, you can do this. No matter if it is character or integer, because we don't have character in reality. So that's how it works. And you see, if there is a character, you do plus plus, it will be the next character. All right, does this make sense? Any questions? If you have any questions, please ask, because we will see more interesting things today. Oh gosh, we have a lot to grasp today. I think we are falling behind. All right. Now that we solved the problem with letters, now how about signed numbers? How about negative numbers? Can we, now that we have only 0 and 1, I don't have anything else, how can I show negative numbers? So for that we have two philosophy, two method. One which people don't use anymore because it wasn't that useful is sign magnitude. In sign magnitude, you say as convention, you say, okay, I'm going to consider the leftmost bit as a sign bit. If it is 0, I'm going to consider that a positive number. And if it is 1, I'm going to consider that a negative number. So 101 in decimal equals to 5. So if it is accompanied by a 0, it is 5, positive 5. If it is accompanied by a 1, it is negative 5. Okay, easy peasy, but it didn't work. So what works basically for us is 2's complement. 2's complement is a different way of showing that. Still, this is sign bit. So in 2's complement, which you will do your activity, everything is based on 2's complement for representing the negative values. It is still the leftmost bit is still the sign bit. So if it is 0, your number is positive. If it is 1, your number is negative. But what negative number that positive is exactly same as sign magnitude, positive side. But what is different is the negative representation. I'm going to give you something that you will not see in the slides, but just to show you, you will need it for your activity or for understanding this. So in 2's complement, what we do is, guys, do you see my paint? Let me check. Yeah, you see my paint. In 2's complement, we basically, so we said that this is, come on, write something for me. Okay. We said that 0, 1, 0, 1. So this is a sign bit. This is a sign bit. So we know that this is a positive number. What is this? So this is binary. This should be multiplied by 2 to the power of 0. This should be multiplied by 2 to the power of 1. This should be multiplied by 2 to the power of 2. So this is 4. This is just 0. This is 1. So it is equal to plus 5. Now I want to write its 2's complement variation. For 2's complement, you invert the bits. First, invert the bits. It means wherever you see 0, you put 1. Wherever you see 1, you put 0. 0 becomes 1, and this becomes 0. Then add 1 to it, which will be, if I add 1 to it in binary, which will be this. How do you add 1 in binary? You just simply say, okay, it's just like doing in decimal. So I add this 1 plus this will be 1. These are zeros, right? Zeros. I just added 1, 1, 0, 1. So for 1, 0, 1, 1 represents -5 in 2's complement. And always you do that. Now, if you want to make this a positive number, again, you invert 0, 1, 0, 0, add 1 to it. It will be 0, 1, 0, 1. Oh, isn't this the same thing we showed here? Yes, it is, sir. So by inverting the bits and adding 1, you convert negative number to positive number in binary or vice versa. You always do the same thing. And this is why it works, because it's simple. Everything in computers is 2's complement. So now let's, is this fine? Is this okay? Please ask questions if you didn't understand. These are important things. You will see later more of these.
Sir, I got a question.
Go ahead, Victor.
For so I understand this example, but what if another number that is given more than 16, like 4 digits?
Very good, very good.
Are we gonna add a number in front of 1?
Okay, very good.
On the first place?
Very good, very good. That's the problem of overflow. We will reach to that. Thank you so much, Victor. Overflow happens when you simply don't have enough bits, enough containers for the number of digits that you want to show. For with 4 bits, we can represent from 0 to 15. As you said, if my number is more than 16, I can simply I simply cannot represent that with 4 bits. That's the problem that happens as defined as overflow. We will reach to that. You simply need a higher container. You will no longer be able to store numbers equal or more than 16 in 4 bits. Then you have to go use 8 bits. You have to. This is basically one of the reasons computers developed. The early age computers were 8-bit computers. Then they became 16, then 32. For a long time they were 32, and then we have 64-bit computers. They have larger containers, so they can keep more data, larger numbers, and all that. Okay, are we good?
So I think, Professor, my question is,
Hmm.
in this example, we compared plus 5 to minus 5, and so the range for this 4 bits is it minus 15 to plus 15?
No, it is not. The range for this, okay, very good question. Very good question. Excellent question. So, look at this. With this, I can represent, oh, don't say. With 4 bits, I can represent 0, 0, 0, 0, and then to 1, 1, 1, 1. In total, I have 16 possible representations with these 4 bits. 4 bits, I can in total have 16 different variations. Right? Now, we said that one of them, if we consider this signed, if we consider this a signed representation, we take the first bit as sign bit. That means I'm left with only 3 bits. And with those 3 bits, I can write 0, 0, 0, 0, which is equal to decimal 0, down to 0, 1, 1, 1, which is equal to 7. Or I can change my sign bit to 1, which will make this a negative number, and I can have this down to this. These are all the possibilities. If you do that calculation, 2's complement calculation, this is -1, this is -8. So with these numbers, with 4 bits, if we want to consider them signed numbers, 4 bits can support from -8 to 7. Not more than that. Is this clear? No answer means probably clear. Now, if we considered this unsigned, so we have the same 4 bits. We have the same 4 bits. Who is not with me here? Let me know. That this is the most important part. And if you understand this, the rest is just a story. Start a poll. Did we understand this? Did we understand this? Okay, Zefi says no. I will explain it. Probably. What part? Can you unmute yourself and tell me what part you didn't understand? And still, Dishdeep, Gurmahak, uh, and many other are not here even, I guess.
I didn't
Uh,
understand like the right part of your paint,
this part?
like the right side of it, the entire part of it.
You
I
mean
can understand like the 0 to 6, like
0 to
0
7? But you didn't
Yeah, I
understand
didn't understand like the
how this
0 to 7.
how this you didn't understand how come this equals to -8? Is that the part you didn't understand?
Yeah.
Okay, very good. Let me explain. So if I just clear this, okay. Let me yeah, here, right here. Let's do the. Oh God, this is not a good tool. Uh, See, 1000. I don't know. By just looking at it, I don't know what number it represents. The only thing I know is that if this is considered a signed number, is if these 4 bits are representing a signed number, the only thing I know that this is a signed bit, and because that signed bit is 1, it means this is a negative number. But negative what? That is what I don't know. Are we good so far? Did you understand until here? Very good. To calculate negative to calculate the value, I know it's a negative number. Well, what number? You have to do that 2's complement calculation that I just explained. Whatever you see here, step 1, 2 steps you require to calculate it. Step 1, invert the bits. I see 1, I put 0 instead here. And I see 3 zeros, I put 3 ones here. Are we good until this? Hopefully, yes. Okay. Step 2, add 1 to that. If I add 1 to this, 1 and 1 will be 2. I cannot show 2 in binary. I put 1 and 1 carry goes here. Again, 1 and 1. I cannot show 2 here. I put 0. I put a carry goes to the next bit. Again, 1 and 1, 2. I cannot show that. A carry goes here. And when I do this calculation, I find the equivalent positive value for this. What does this value represent? Sorry, wait a second. Yeah, what does this represent if it was an unsigned value? This you multiply this by 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. What is 2 to the power of 3? Isn't it 8?
It's 8, yeah.
Exactly. After these 2 steps for 2's complement, when you convert that to positive, you see that the positive unsigned equivalent is 8. That means that number was -8. You can do the same thing to 1 1 1 1. You will see its positive equivalent will be 1, and because of that, this num 1 1 1 1 represents -1. Is this clear now? Do you want me to do that, or you think you can do it? You can do it right now by yourself.
Yes, sir, it's clear.
Clear. Very good. Very good. Thank you. Good question. Very good question, guys. Don't let your questions stay in your mind. Tell me what your question is, and I'll do my best to explain. Okay. So this is how we represent negative numbers in 2's complement. And now you admit that if we didn't we have 2 options. We either consider this 4 bits as a signed number or an unsigned number. you admit that if this wasn't signed, we could fit in these 4 bits from 000 to 1111. If this wasn't signed, then this wouldn't be a signed bit, and the whole thing could be converted to decimal, which would be 0 to 15. 0 to 15. You see the difference? 4 bits represent -8 to 7 if we consider it signed. It can represent 0 to 15 if we consider it unsigned. By considering things signed, we are using 2's complement, and we are considering the leftmost bit as a signed bit. That's all I wanted to say. Are we good now? Okay, let's go back to our slides and see some stuff. So this is how we represent. Guys, whenever you see all ones, because of the reason I just showed you, when you see all ones, now we have instead of 4 bits, we have 8 bits. Whenever everything is 1, that represents 1. At home, do that conversion, 2's complement conversion tool that I just gave you. Do that and see what this represents. Can invert the bits, add 1. See, the positive equivalent for this will be 1. Because positive equivalent is 1, then this is -1. And so on and so forth. Okay, now, even more crazy things. What happens in C programming if you have both unsigned and signed numbers and you go ahead and compare those? Let's see an example. Now it takes me to this line. First of all, you can have a number. This in binary. Let's see what this is in binary, guys. I have, this is in decimal. But if I want to show it in binary, I just put it in decimal, 4294967295. You see, I have all these bits are 1. So it is 1, 1, 1, 1, 1, 1. What does this represent in this case? If it is all ones, what does this represent if I consider this signed? Somebody answer this question, please. I'm repeating the question. What will I see here when when I treat this number as a signed number, and what will I see here? If it is, and considering that the binary representation of this is all ones, everything is 1, 1, 1, 1, 1, 1, everything is 1. Can somebody answer? It's easy to guess. Let's see. Nobody answered. Let's see. I'm just running this code. It's taking me a while. All right, guys, look at this. Another shocking thing that might put you in a big trouble later in your code. Look, I defined integer and I put this value in that. When I show this as an integer, when you put d, it means signed integer. It is equal to -1. It was easy to guess because I said whenever all the bits are 1, it is -1 because of that 2's complement thingy that we just talked about. But if you consider it unsigned, the compiler's output will be that number. So you have some number there, but it's just all acting crazy different. If it is signed, it's something. If it is, and it's not just magic, it's C programming, it's Visual Studio. I'm just writing the code. Another interesting thing. Now look at this. Let me uncomment this. Now, when it comes to comparing signed and unsigned bits, what do you think will happen? I'm just uncommenting this piece of code. There we go. Now, I will take a poll on this, on the answer for this. So be careful. I have an unsigned integer. I have defined an unsigned integer UI. I have put this, the value that you saw here. I have an integer which is this. If you don't say anything, it is signed. So if you don't say signed integer, these are basically the same thing. Signed integer or integer, they're both the same thing. Signed integer I, integer I equal to -1, signed integer si equal to -1. Which one of these outputs do you think you will see if I run? If UI, if 4, 2, blah, 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 4 billion, 2, blah, 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 I can't even read that. If this number, is this number equal to this number or not? Which one will I see? Will I see this one, meaning that UI and I are equal, or I will see this, which apparently I'm expecting to see. I don't know which one. Which one do you expect to see now if I run this code? Let's run a poll. Will you see this? I wasn't expecting this, or you will see correct. Go ahead and answer, please. Which one will we see when I run this code? Will we see this message, I was not expecting this, or we will see correct? I guess people are thinking, which is good. Okay. Good. I'm just publishing the poll. We have people saying either of them can possible. Like some people say, I was not expecting. Some people say corrected. Now I'm gonna run this code. Here is the result. Oops. I was not expecting this. Were you expecting UI to be equal to I while UI is this and I is this? Are these equal? Yes, they are. How they are equal? They are, well, actually, I had to put this, actually. We will see the same thing. Because the representation for this in signed is 1, 1, 1, 1, 1, 1. And the representation for this is also the same thing, 1, 1, 1, 1, 1, 1. So because they are signed and unsigned and the binary representations are the same, we see the same thing. Surprise, isn't it? Now let's go. So we learned some lessons. I think now we're falling behind. We are learning something from this that we should be careful. First of all, signed and unsigned matters. when you are writing your code. And in some of these data types, the number of bits you have also matter. So these are the things that we are learning. To be able to show to be able to define integers with different number of bits, we have to do differently, because by default, if I say int, depending on my platform, which is my hardware and operating system, the number of bits that will be allocated, see, this is where operating system and the platform becomes important. Depending on your platform, your int will have different number of bits. How you can see that, how you can figure that out, you can just simply write this. You can say size of will take care of that for you. For example, if I write size of int here, size of int, and let me just uncomment everything else. Sorry, comment everything else so that we see this only. Okay, if you run this, this will show the number of bytes that is allocated to that automatically Windows allocates to that data type, which is here integer. Integer has 4 bytes. Now, if I change this to something that we see here, if, by the way, in this slide it says if you include this std int dot header or int types header, you will be able to define integers of your desired size. For instance, if I want to make this int, which is by default 34 bytes, 32 bits, I can, if I want an 8-bit int, you should, by adding those header files, you can say uint the size int and then t. So this makes it an 8-bit integer. So now if I run this, the number will be 1 byte. So this, if when I change this, now it's a 1 byte. It's 8 bits. Now you see the importance of these. So by defining these, by including these header files, either int types or std int, you will be able to define int of desired size. 8-bit you want, 16-bit you want, 32-bit you want, things like that. So if we continue, we will reach to overflow. Overflow, what is overflow? Overflow is a problem that happens when you don't have enough bit to store the result of a calculation. For instance, look at these calculations. You subtract 128 from 127. The result is correct. Okay, -1. This is okay. But this one's not okay. Guys, look at this. We are doing signed arithmetic. So 127 plus 1 is 128. But just because we don't have enough bits here, your computer considers this a sign bit, right? We said that this is a sign bit. And because it is a sign bit, if you do that calculation, 2's complement, you will see that this is -128. That's a big problem. I just added 1 to 127 and the result is a negative number. This is an overflow. Overflow happens when you are expecting a positive value, but you receive your result is negative, or vice versa. You are here, like here. Negative 128 minus 1. The result should be negative 29, but it is positive 127. How come this happens? This happens because we don't have enough container. If I just had another extra bit here, this wouldn't happen. Now, let's see on our code. I have defined, let's see if it is real. It's not just on the slides, it's in real programming language. Now, look at this. If I want to do this. So, if I had to, because the problem happens when I don't have enough bits, that's why I have restricted my int type to 8-bit. Okay, with the method that I just said. So now I'm adding 127. It's an 8-bit integer. I'm adding 1 to that, and I'm showing the result. Now let's see what the result is. And this is, by the way, placeholder for showing that 8-bit representation. There's nothing magic here. And if I run this, as the slides also showed, the result will be negative 128. But this problem wouldn't exist if we had enough bits. So if I just change it to 16, change this to 16, change this to 16. And I guess this should be 16. No, let me run this. I'm not sure about this though. No, I guess it should be also 16. Let's do something. Let me just say this is int, which means I have 32 bits. Int 32 bits. Enough bits, right? Int is by default, as we said, 32 bits. This will not happen. And here I simply put a D. I simply put a D and just do this. Okay, now let's run it. Now the result is positive 128. That's what we were expecting. So because of this number of bits, the limited number of bits that I had, this was happening. Now imagine you're working with larger numbers, close to the limit of your 32-bit container, which is this int. You will see this problem. So what we learn from these in programming, first, be careful about overflow. Overflow can happen if you are working with large numbers, or the type of variable is just 8-bit or limited number of bits, 16 bits. In each of these types, a specific range of numbers can overflow, which can result in nonsense. Another thing, signed or unsigned matters. You never compare signed with unsigned. You have to compare signed with signed or unsigned with unsigned. And this is showing the same thing we had. This is the same code. I have put the code in a slide so that you can practice at home if you want. And type of integers that we have, these are the typical names we give them, but you can do this uint. If you add these libraries, you can do uint 8 or 16 or whatever. And here the names that we give them is, for 8-bit integer we call it byte. If it is unsigned, it can represent this range. If it is signed, it can represent this range. Why? I explained the reason for a 4-bit. 16-bit, it is called short. This is the range for signed. This is the range for unsigned. 32-bit called long. This is the range for unsigned. Here, this is the range for unsigned. This is the range for signed. And long 64 bits. This is the the range is much larger than this, so I just didn't put it here. This makes it slow. This makes the calculation a slow 64-bit, unless your platform is 64 bits, which these days is mostly is. One real world problem, nice Gangnam Style video. It got viral, and YouTube had to think for the first time the number of viewers growing more than 4.2 billion, which could possibly be stored in an in a 32-bit integer. And for the first time, YouTube had to revise its code and go to 46 bits. So these things happen in real life. Uh, this is what you will have in your a similar question in your activity. Uh, what if we have a counter that tracks hundreds of a second? Let's first look at this. This is an interesting website. You can refer to this. This is Unix Epoch. This is a standard website that started counting in this time and at this date. It started counting, and every time it is adding one epoch or one number every second. Every second it's adding one epoch to the value of the counter, and this is a 32-bit number, and that 32-bit number, and 32-bit number will run out of enough space at this date in 2033. This will go back to zero again unless they revise it and add this. So that epoch, you can in your code you can refer to that. That's kind of a universal clock. You can refer to that epochs, and you can calculate exact time in your code if you need. So think about it. Why with 30? If I have a 16-bit integer, how long will it take if I'm ticking every hundredths of a second? How long will it take for this to overflow? Think about this. And floats and doubles. Floats and doubles. Again, I said we don't have any other choice except for representing floats and floating numbers with zeros and ones. That's how we represent them. Double has 15 meaningful digits after the floating point, but float has only 6. So it's basically more precise. Uh, be careful when you are using float and double. Again, like signed and unsigned, they shouldn't be compared. Let's go back to our code, and now I'm gonna comment out this part, and I'm gonna comment out this part. Now I have a float that is 1 divided by 6. This is how you show the precision. So let's make it 6, and I'm gonna show 6 digits. If I run, I'm gonna show 6 digits the after the floating point. Uh, what is wrong with it? Did I receive an error? Oh. Equal to this. Okay, so this is the result 1666667 with 6 uh, digit precision. You can play with that and change it, but what I'm going to show you is this part. Now we have a double. We have defined a double, which is still the same, showing that double and float are for decimal point numbers. I have defined float 1 divided by 6, and I have defined double d1 1 divided by 6. What do you think will happen if I compare these 2. Will this be comparison successful or comparison is nonsense? Is this equal to this, considering all these conditions? Yes or no? Is this equal to that? Start a poll. Start a poll. Is this, will the equivalent will be okay or not okay? Yes or no? Are these two equal or not? I guess the answer is obvious after all the things that I have discussed. Well, oh no, we have two completely different type of people. So once more, I have defined float and I have defined double. Both of them are keeping the result of 1 divided by 6 in decimal points. Let's run. Comparison is nonsense. It means these two numbers, f1 and d1, are not equal, even though they both keep the result of 1 divided by 6. But since it is keeping that number with 15 digits precision, and this one is keeping with 6 bits precision, when those bitwise representations are compared, this has some more digits, some non-zero digits than this. So literally they are not equal. That's why in comparing floating points, and first of all, never compare double to float. And for comparing floating point numbers, you cannot do this if this is equal to this. This is nonsense. You have to take the difference, and if the difference within in a specific boundary, the difference of these two is in a specific boundary that you define, then you can consider them equal. That's how it is. Let me see what else we have in our lectures, and I will answer questions, guys. Don't worry. Why did it reach here? Okay, so some critical problems, some real life problems. I cannot just explain these things. You can go through and go through the slides. See, there some real problems. Ariane 5 was a big failure because of this conversions, things like that. So in your code, be careful. Number of digits matter. Precision matters in float numbers, and signed and unsigned matters. So be careful about those. And if you want to catch an error, it is a good practice to have conditions like this, either with if else or with switch case, so that if none of those cases are correct, you show the error to yourself or to the user, so that they know things didn't go as expected. So error traps is always a good practice. And I'm going to show you what this overflow, what kind of serious problem. This is also activity question, so be careful. Listen to this, guys. We have to imagine we have a problem of searching for something. So imagine we want to search for 37, and these numbers, some probably random numbers, are put in an array, and we have two choices, two options, two typical point. We want to find which index is this 37 in. One way is sequential, so you go ahead and look at these places one by one until you reach 37. Another way is look at the beginning, look at the end, and then compare the begin and end. See, that number is closer to which one? If that number is closer to the number at the end, and obviously these are sorted, so it wouldn't work without sorting. So imagine we put them there, the numbers there, and we sort them from low to high. And then in this technique, in the binary search, we see if it is closer to the one at the end, we just don't search the first half anymore. We find the middle, and then again in that middle we look at the middle and the other number, we see which one it is closer to, and so on and so forth. This video shows how it is work, and also in your activity there is a link that will send you to even a better animation. So this is the difference. Why do we use binary search? Because it's faster. See, it found 37 in 3 steps, but this one binary found it in 9 steps. So we like to do binary search, but sometimes when you are doing when you are trying to find that mid, meaning that you are doing this high plus low divided by 2, this overflow might ruin everything. This is the question from you in the activity. In what cases this can ruin your life, and what do you suggest for that? Okay, no more on this because this is activity exercise and you will do it. Hexadecimal, guys, hexadecimal 16 by 16 is another representation form for binary and decimal. Why we like it? Because it is simpler, and what we do is basically simply if we know the binary representation, we divide them in 4 by 4, we separate them in groups of 4 and write the equivalent value for that 4. So here this is 0 plus 2 plus 4 plus 8, which is equal to 14. That's why there is a e here. And this one is equal to 1 plus 2 plus 4, which is 7. So this binary is equal to 0x. 0x is a symbol showing that this number is in hexadecimal or hex, and this is 7e. Now look at this. This is 1 plus 2 plus 4 plus 8, which is equal to 15, and we show 15 by f in hexadecimal, and this is the same 7. So this is how we convert those, and this comes useful in doing color coding. For instance, if I show you, this is also in your exercise. So if I sorry, I went a little bit quick, I think, here, but in Word, if I open a Word file, an MS Word file, and want to do this, the all the colors, you definitely know, all the colors that we create are created using only red, green, and blue. Depending on how much I want red in this, how much I want green, or how much I want blue in this, that will be different. So test test color test color test. I want to give a color to this, so you can select from here more colors, and in more colors you can go custom. In custom, you either give the binary equivalent from 0, any value from 0 to 255 to this. Let's try 255. 0, see, it gave me error. 255 is basically the highest intensity of that color, and 0 is nothing. So if I put 0 here, in the combination there is no red, But if I put 255, I have red. 255, 255. If everything is 255, we have all the colors, and that creates white. And you see the equivalent hex here. You can use this tool for your activity. You can use MS Word. So there are some numbers. If we give here, you see the hexadecimal equivalent, which is useful in styling in CSS, basically CSS styling websites and stuff like that. And this is one of the applications of hexadecimal. So hexadecimal, how to you convert to decimal, and how you create colors out of that. This is basically the last slide, and the rest will not be. We have some other slides. Go read them. They will not be in the quiz though. Uh, so let me see. Do you have any questions, guys? Are we good? Let's have a 5-minute break, and the last thing we will see is a nice presentation by Simrat. She will be here. You can ask questions after that presentation. So, guys, please come back in 5 minutes. And if meanwhile, if you have questions, please ask. Any questions? Okay. Any questions? Is a Paul. Any questions? Okay, very good. People are responding. People are here. Very good. Today we have a presentation by Simrat Kaur. Thank you so much, Simrat. Let's see what her topic is and what she's interested in. And I'm gonna run her video presentation. Okay, sorry. I think I also need to share system audio.
fate and life of a star depends primarily on its mass. So astronomers has developed many kind of information about stars using the information technology. Let's see further how they use it. Firstly, the knowledge that we knew about stars from the very ancient era. Since 1955, it has been assumed that the composition of stars in the universe, other galaxies, is similar to that of the hundreds of billions of stars within our own, a mixture of massive, medium mass, and low mass stars. But with the help of observations by telescopes from 1,40,000 galaxies across the universe and a wide range of machines that IT has provided today, the team has tested whether the same distribution of stars apparent in the Milky Way applies elsewhere. The answer is no. Stars in distant galaxies are typically more massive than those in our local neighborhood. The finding has a major impact on what we think we know about the universe. Study of stars. Information technology invented the Spitzer Space Telescope in 2003, but researchers of Neil Bohr Institute assumed that the size and weight of stars in other galaxies was similar to our own for more than 50 years. They use many information technology like cameras, spectrographs, and interferometers for the study. In this study, the researchers analyzed light from 1,40,000 galaxies using the Cosmos Catalog, a large international database of more than 1 million observations of light from other galaxies. These galaxies are distributed from nearest to farthest reaches of the universe, from which light has traveled a full 12 billion years before being observable on Earth. Now, the latest information about stars. According to the researchers, the new discovery will have a wide range of implications. For example, with the help of Hubble Space Telescope, it remains unresolved why galaxies die and stop forming new stars. The new results suggest that this might be explained by a simple trend. Now that we are better able to decode the mass of stars, we can see a new pattern. The least massive galaxies continue to form stars while the more massive galaxies stop birthing new stars. The center is dedicated to understanding when and how the first galaxies, stars, and black holes formed and developed in the early universe through observations using the largest telescope along with the theoretical work and simulations. So, all the studying that was done by the astronomers of the Niels Bohr Institute have made it possible and have made true that fact that stars are heavier than we thought. So they use many kind of technology to study this fact, which is listed below, like sonar, Hubble Space Telescopes, radio dishes, CCD cameras, filters, photometers, spectrometers, spectrographs, interferometers, high energy practical detectors, low energy charged particle detectors, plasma instruments, dust detectors, magnetometers, plasma wave detectors, planetary radio astronomy instruments. And there were many more, so I can't list them. So this was all about my presentation. I hope you liked it.
Okay. Thank you, Simrat. It was interesting. Astronomy is one of my own interests. I'm really passionate about it. I think you've all heard about new James Webb Telescope, and everybody is waiting to see finally what will the discoveries be. In terms of ICT, just think about uh, just a simple question. Just think about what is the programming language they use to program all these hardware and software, communication, stuff like that. So complicated. So it's all interesting. Probably to make things more precise, they use Fortran. Just kidding. But it is interesting, and thank you so much, Simrad. I really enjoyed it. Other people, if there is any question from Simrad, you can ask. She's here to answer. If no, I wish you a wonderful week. Activity will be available in half an hour, and you will have time to submit it by the end of Sunday night. And don't forget to do quiz. Sunday 1 p.m. start, Monday 1 p.m. It will be unavailable. Thank you so much. See you next week.